Hi everyone and welcome back. In today's video, you'll learn about hypothesis testing and all the concepts revolving around it. So drink some coffee, some tea, or whatever substance you drink to stay focused because this might be a pretty long video. The prerequisites are having a basic understanding of probability distributions, the normal distribution, and the central limit theorem. If you haven't watched my videos on these, you'll find them. You'll find the links in the description box. Now, without further ado, let's get into it. This video covers a lot of topics related to hypothesis testing. You're going to learn a lot today. You're going to learn about the standard error, the null and alternative hypotheses, level of confidence and level of significance, rejection region, critical value, test statistic, p-value, type 1 and type 2 errors, and last but not least, confidence intervals. Let's begin with a few quick reminders to go through this tutorial under the best possible conditions. First off, remember that when a random variable is normally distributed, it is easy to estimate probabilities thanks to the properties of the normal distribution. One such variable can be standardized by converting its values into z-scores so as to turn its probability distribution into a standard normal distribution with a mean of 0 and a standard deviation of 1, and then use the z-tables which contain pre-computed probabilities for each possible z-score. For example, if you want to know the probability of observing a particular x value, you can use the z-tables that will tell you what the probability for this particular x value is. And the z-score of a particular x value is calculated using this formula. So this is for population data. For sample data, it's a little different. We subtract the mean from a particular value of x, and we divide the difference by the standard deviation of the population. And a z-score is just a measure that tells you how many standard deviations a particular x value is away from the mean. For example, an x value with a z-score of 2.5 means that this particular x value is 2.5 standard deviations away from the mean. Often when we don't have access to data from the entire population on the study, we take samples. We calculate the mean of each sample. In other words, the sample mean, and we work with these sample means instead of working with the raw data itself. Some widely used statistical tests consist of comparing sample means, and they are performed using the probability distribution of the sample means, also known as the sampling distribution of the mean. If the sample size is large enough, usually over 30, the probability distribution of the sample means, aka the sampling distribution of the mean, like I said, approximates a normal distribution. Finally, the CLT, the central limit theorem, states that the mean of the sample means is equal to mu, the population mean, which oftentimes is unknown. And if you don't know mu, the population mean, you can get a pretty good approximation of it by using this property of the CLT. So you take a bunch of samples, you calculate the mean of each sample, and then you calculate the mean of these sample means, and the mean of the sample means is going to be very close to mu, the population mean. You can also compute the standard deviation of the sample means, also known as the standard error. If you didn't know what the standard error is, now you know. And it's equal to the population standard deviation sigma divided by the square root of n, where n is the sample size. So that's, again, according to the CLT. From this, you can also infer sigma when it is unknown. When you don't know the population standard deviation, you can get a pretty good estimate by multiplying the standard error by the square root of n. You can also compute z-scores for sample means using this formula. So we subtract the mean from the sample mean, so mu, the population mean, or the mean of the sample means, from a particular sample mean, and we divide the difference by the standard error. Now let me give you a definition of hypothesis testing. Hypothesis testing is a statistical procedure in which two statistical measures are being compared, usually means or proportions, and a null hypothesis is tested against an alternative hypothesis, where the null hypothesis, denoted H0, is the default assumption, and the alternative hypothesis, denoted H1, is the challenging assumption. Whatever the null hypothesis states, the alternative states the opposite. H0 and H1 are mutually exclusive assumptions. If the null hypothesis states that a sample statistic is equal to a measure currently accepted as the true measure, then the alternative is going to state that this sample statistic is different from the measure currently accepted as the true one. If H0 states that the sample statistic is less than the measure currently accepted as the true measure, then H1 is going to say that the sample statistic is greater than this value, etc., etc. You get the idea. And the possible outcomes of hypothesis testing are either we reject the null hypothesis because we have enough evidence to reject it, or we fail to reject the null. We don't reject the null hypothesis because we lack evidence to reject the null. So the whole hypothesis testing process can be split into 4 steps. Step 1, we define the null and the alternative hypothesis. Step 2, we choose the significance level or level of significance, usually denoted with the Greek letter alpha. Step 3, we compute the test statistic, and the test statistic is just a sample statistic that we're going to turn into a z-score. For example, if our sample statistic is a sample mean, then we are going to standardize this sample mean and we're going to compare it with a critical value to check whether this sample mean falls in the rejection region or not. Step 4, we compute the p-value and we interpret results. If our test statistic falls in the rejection region, we reject the null hypothesis, and if it falls in what's called the non-rejection region, then we do not reject the null hypothesis, and in which case we say that we fail to reject the null. Now let's say we have a population under study whose population mean is unknown. We don't know the population mean, perhaps because the population is huge and we cannot compute the mean nor the standard deviation. But we have a hypothesized mean that is believed to be the actual population mean. And yet we need to prove this statement. So we plan to take a sample to calculate the sample mean and to compare this sample mean to the hypothesized mean. We define the following statements. In our null hypothesis, we state that the sample mean is equal to the hypothesized mean, and if that statement holds, then we can trust the hypothesized mean to be the actual population mean, or at least very, very close to it. In the alternative statement, we say that the sample mean is going to be different from the hypothesized mean, that there's going to be a statistically significant difference between the sample mean and the hypothesized mean. We don't say that the sample mean is going to be greater or smaller than the hypothesized mean. We don't know. Once the null and the alternative hypothesis have been defined, the next step consists of standardizing our data. We're going to standardize our sample mean and then use the standardized version of the distribution of the sample means, where we are going to put the hypothesized mean at the center, which makes sense because the central limit theorem says that the mean of the sample means, this is the distribution of the sample means, and the mean of the sample means is at the center because this is a normal distribution. Since the mean of the sample means is equal to mu, the population mean, and since we assumed that the hypothesized mean is the actual population mean, it makes sense to put the hypothesized mean at the center. And we're going to see where our sample mean, our test statistic, falls in this distribution. If it falls far away from the center, from the hypothesized mean, we are going to reject the null. And if it falls close enough to the center, then we are going to assume that the null is true and we are not going to reject it. But where do we draw the line? Where do we say that here we reject the null and here we do not reject the null? We must define the area under the curve in which we will not reject the null hypothesis if the sample mean falls there. And we need to define where this area starts and how wide it is. To know where this area starts, we need to look at our hypothesis. The alternative hypothesis states that the sample mean is different, so it can be smaller or greater than the hypothesized mean. Therefore, our non-rejection region starts from the middle of the distribution and extends both to the left and to the right. And the area that will remain is going to be split in the two tails and is going to be our rejection region. So we're going to have two rejection regions, one in each tail. Now remember when I said in the normal distribution video that about 95% of data falls between -2 and +2 standard deviations from the mean. Here, since we are dealing with sample means, it's between -2 and +2 standard errors from the mean. Well, it is actually 95.45% of data to be precise. 95.45% of data falls between -2 and +2 standard errors from the mean, whereas 95% of data falls between -1.96 and +1.96 standard errors from the mean. These two z-values or z-scores mark the lower limit and the upper limit of our non-rejection area. The area under the curve in which it is okay for our standardized sample mean to fall without leading us to reject the null hypothesis. And the width of this non-rejection region is defined by the level of confidence. Here we have a 95% confidence level. Sometimes you'll see 90% or 99% confidence levels. And whatever probability remains in the tails, in the left tail and the right tail, is called the level of significance, which is equal to 1 minus the level of confidence. So 1 minus 95% gives us a level of significance of 5%. And this level of significance defines our rejection region. So we split this probability in the two tails. So we get a 2.5 probability in the left tail and a 2.5% probability in the right tail. And if our test statistic falls in one of these two regions, we reject the null hypothesis. If it falls in the non-rejection region, we assume that the null is true. And the p-value is just the probability of observing a test statistic that is as extreme or more extreme than the one observed. Now listen carefully. When I say as extreme or more extreme, I mean in both directions. So the p-value is the probability of observing a test statistic that is as small or smaller than minus 2.33 standard errors, plus the probability of observing a test statistic that is as big or greater than 2.33 standard errors. So we double the area we see here on the left. We double the area we see to the left of the test statistic here because we take into account both directions. In the second possible scenario, our null hypothesis states that the sample mean is less than the hypothesized mean for whatever reason, and the alternative states the opposite. The sample mean is greater than the hypothesized mean. Therefore, we must expect our test statistic to fall somewhere here in the right-hand side part of the distribution. Again, we define our confidence level to be 95%, and the non-rejection region goes from -infinity all the way up to this critical z-value here. The significance level is again 5%, it doesn't change, but this time we have more probability located in the same tail, in the right tail. Therefore, the critical z-value here is no longer 1.96, it's less, it's 1.645. Again, if our test statistic falls in the non-rejection region, in other words, if it's less than the critical z-value, we must assume that the null hypothesis is true. We fail to reject the null. And if our test statistic falls in the rejection region, we reject the null hypothesis. And the p-value is, again, the probability of observing a test statistic as extreme or more extreme than the one observed. In this case, it's the probability of observing a test statistic as big or bigger than 2.66 standard errors. It's the area under the curve to the right of the test statistic. So it's the area under the curve here, the white area under the curve. And that was it for our right tail test. So far we've seen the two-tail test, the right tail test, and the third possible scenario is the left tail test, which we are going to perform using a practical example as our guiding thread. So we're going to perform this test step by step, and here's a bit of context. About 188,000 people are living with brain cancer in the US. So these people are our population, population of size 188,000. A pharmaceutical company developing a new drug A claims that drug A reduces brain tumors by at least 80% on average. We want to test the effects of this new drug A on brain tumors by evaluating the average percentage of tumor reduction achieved with drug A against the claimed average percentage of tumor reduction, which is 80%. We select a random sample of 2,000 patients having brain cancer. We give them drug A, so our sample size N is equal to 2,000. We measure the percentage of tumor reduction for each patient. We calculate the sample mean, so the average percentage of tumor reduction in that sample. And suppose that this sample mean x bar is equal to 50, so we observed a 50% tumor reduction on average in this sample of 2,000 people with a standard deviation of 15%. Now you may ask, how do we build the probability distribution of the sample means if there's only one sample and therefore one sample mean? Don't we need the standard deviation of the sample means, aka the standard error, to define this distribution? How do we compute a standard deviation of sample means if there's only one sample mean? Well, we can't. We can't always take many samples. Sometimes for cost and safety reasons, we can only work with one sample. And obviously, we can't test the drug on everyone with brain tumors. What we can do instead is get a theoretical estimate of the standard error using the following formula. This formula is given to us by the central limit theorem, which states that the standard deviation of the sample means is equal to sigma, so the standard deviation of the population, divided by the square root of n, where n is the sample size. In this case, it's 2,000. So like I said, the standard deviation of the sample means is more commonly known as the standard error. Here we don't know sigma, we don't know the standard deviation of the population, so we must use the sample standard deviation, S, which is equal to 15 in this case. We're going to use it as our best guess for sigma. Now we can use the hypothesized mean, which is 80%, and the calculated standard error as parameters to define an approximation of the probability distribution of the sample means. So it's going to be an approximation, not the true probability distribution of the sample means. because again we used a sample standard deviation instead of sigma, and use this distribution to find the probability of observing a sample mean equal to 50 under the assumption that the null hypothesis is true. The stage is set. We can now proceed with the test itself. Step 1, we define the null and the alternative hypothesis. The currently accepted average percentage of tumor reduction is the one claimed by the pharmaceutical company, 80%. So in our null hypothesis, we state that the average percentage of tumor reduction in the sample is greater than or equal to 80%. We think the claimed percentage is too optimistic, that the true average percentage of tumor reduction achieved with drug A is less than 80%. Therefore, in the alternative hypothesis, we state that the average percentage of tumor reduction is less than 80%. In step 2, we choose the significance level, which remember is equal to 1 minus the confidence level. For this example, I'm going to stick to a 95% confidence level. Therefore, the significance level is 5%. It's the remaining probability. The non-rejection area goes from positive infinity to this critical z-value here, minus 1.645 standard errors. The rejection region is located on the left, which makes sense because in the alternative hypothesis we state that the sample mean is less than the hypothesized mean, so we expect the test statistic to fall somewhere here in the left-hand side part of the distribution. That's why we call it a left-tailed test. Now, keep in mind that if you change the level of significance and therefore also the confidence level, the two are tied, the critical z-value is going to change too. So you need to look up the critical z-value corresponding to the chosen level of significance. In step 3, we calculate the test statistic, which in this case is a standardized sample mean. Given that the currently accepted average percentage of tumor reduction denoted mu is 80, that the sample mean x bar is 50, that the sample standard deviation denoted S is 15, that the sample size n is 2000, and that the standard error is equal to the sample standard deviation S divided by the square root of n. Our test statistic, which is commonly called the z-statistic because this is a z-test, and which you can also call the z-score of x bar. X bar is our sample mean, is equal to x bar minus mu divided by the standard error, which in this case is equal to 50 minus 80 divided by the standard error, divided by 15 over the square root of 2000. That gives us a negative 30 over 0.3354. And finally, our test statistic is equal to negative 89.44. In step 4, we find the p-value and we interpret results. We've just calculated the test statistic, so let's see where it falls in the distribution. It falls very far from the center of the distribution, from the hypothesized mean. Our sample mean is almost 90 standard errors away from the hypothesized mean. And the p-value, which is the probability of observing a test statistic as extreme or more extreme than the one observed, in this case the probability of observing a test statistic that is as small or smaller than a negative 89.44 standard errors, is very, very close to 0. So the p-value is the area under the curve to the left of this test statistic here. We can't even see it on the graph. It's too small. It's very, very close to 0. It's less than 0.05, our level of significance. Therefore, we reject the null hypothesis and we admit that the hypothesized mean may not be the actual average percentage of tumor reduction in the population. At this point, we've performed our test and we've rejected the null hypothesis. But what are the possible implications of this test? Well, in the first place, the new experimental drug A might never be commercialized. But what if we are wrong? What if our test was badly performed? That's where type 1 and type 2 errors come in. Remember that our null hypothesis stated that if we were to take a sample of n people and give them drug A, the average percentage of tumor reduction would be at least 80%, and the alternative stated the opposite. The average percentage of tumor reduction was to be less than 80%. So there were 4 possible scenarios here. In the first scenario, we didn't reject the null hypothesis, and since it was actually true, we made the right decision. In the second scenario, we rejected the null hypothesis, and it turned out to be false. So again, we made the right decision. In the third possible scenario, we rejected the null when it was actually true. So we made a type 1 error. And finally, in the fourth possible scenario, we didn't reject the null hypothesis when it was actually false, and we made a type 2 error. So to recap, the type 1 error is made when you reject a true null hypothesis, and the type 2 error is made when you when you fail to reject a false null hypothesis. That said, what's the difference between type 1 and type 2 errors? Which one is worse? Well, it really depends on the context. In our example, we rejected the null hypothesis, so we either made the right decision or we committed a type 1 error. Suppose drug A is the only drug effective in prolonging patients' lives and its side effects are entirely tolerable even for patients with early-stage brain cancer. Then, because we committed a type 1 error, this drug is not going to be marketed, and a lot of these patients are going to lose months or even years of survival time. Whereas if we had made a type 2 error, the consequences would have been less serious since the drug's side effects are not too severe. By contrast, if the side effects of drug A are severe, if they are truly harmful and potentially life-threatening, and we committed a type 2 error, then lots of people who could have survived much longer without drug A are going to die quickly. Final chapter of this video, let's talk about confidence intervals. When performing hypothesis testing, we assume that the hypothesized mean is the true mean of the population, so we put it at the center of the standardized distribution of the sample means. Then we compute the test statistic and we check whether or not the test statistic falls in the rejection region. Whereas when building confidence intervals, we put the sample mean x bar at the center of the distribution of the sample means, and we say that we are 95% confident that the true population mean falls within this confidence interval. And a confidence interval is just a range of plausible values for the population mean, which remains unknown. We don't know if the true population mean is going to fall here or here or here. We don't know if this 95% confidence interval is going to contain the true population mean, because a confidence interval is built around a sample statistic. It's built around a sample mean in this case. So it's built for a particular sample. But when we have a population and we take many samples from this population and we calculate the mean of each sample and the standard deviation of each sample, these samples are not going to have the same means. They are not going to have the same standard deviations. They are not going to have the same variability. And yet, if we take a sample, compute its mean, its standard deviation, and use these parameters to define an approximation of the distribution of the sample means, and then calculate a 95% confidence interval for this particular sample, and then we repeat the process 100 times, then 95 out of these 100 confidence intervals that we calculated would contain the true population mean, and 5 wouldn't. That's the definition of a 95% confidence interval. To end this video, let's actually calculate a confidence interval for a sample in the case of a two-tailed test. A confidence interval is composed of two values, the lower bound and the upper bound. In this case, the lower bound is equal to the sample mean minus z times the standard error, and the upper bound is equal to the sample mean plus z times the standard error, where the sample mean is equal to 50, z is 1.96, so z is our critical z values. The standard error is equal to the sample standard deviation divided by the square root of n, where the sample standard deviation is equal to 15, n is equal to 2000. The standard error is therefore equal to 0.3354, and z times the standard error is equal to 1.96 times this value, which gives us 0.657. Therefore, our confidence interval is equal to 50, the sample mean, minus this value, z times the standard error, comma, 50 plus 0.657, and that gives us a confidence interval of 49.34, comma, 50.657. That's how we calculate a confidence interval. I guess that's the end of this one. If you liked it, know that these videos represent a lot of work. This video alone took me 2 weeks. It took me 2 weeks to make this video. And I mean, it doesn't cost you anything to click on a button. So please share, like, comment, and subscribe to my channel. I would really appreciate it. That would help me a lot. You can also support my channel by buying me a coffee. You'll find the link in the description box. Again, thanks for watching and see you in the next one.